Hi. In this video, we're going to go over the physics journal, which is about the energy bar charts. The question that's kind of guiding us is how can you visually represent the energy transfers and transformations? So basically what that means is like, as if we take a certain situation in which the energy is changing, how do we change, like how do we keep track of that? Because we start out with one kind of energy, maybe energy is added or subtracted, and then maybe we end up with a different type of energy. How do we keep track of all that? So the big idea here is the energy in a situation can be represented using bar charts. So let's just recall that a bar chart, looks each one of these. So I've got like basically two different bar charts. I've got an initial bar chart on the left here. So as we look at the diagram here, it shows, let's see here, right? It shows that I got a little spot where I could put kinetic energy. I got a spot where I could put gravitational energy. I got a little spot where I could put elastic energy. So, maybe let's just say like, someone's, pedaling a bicycle or something like that. Or let's say someone's sitting there, um, you know, just trying to think of a situation here. Let's say someone's on the top of a hill, riding their bike at the top of a hill. So, or they're at the top of the hill, but they're not riding their bike. So they're at the top of the hill. So maybe they've got some gravitational energy or something like that. Again, it's a person on a bicycle. So let's just so we would include like what type of energy do they start with um, in that spot right there. Then we got this work done. So like if there's any energy that's being added or subtracted, right, that would take place, here. So I could, if maybe then the person like pedals the bike, obviously that's going to add energy, into the system there. Let's talk about what we mean by a system real quick. So it defines what is in the system. So, like sometimes there's just one thing in the system. Like in this case, we're just talking about the bicycle. Um, and so you would then inside that circle list what are the things you're keeping track of the energy for. So like in this case, because it's a person, like again, it's just a situation I'm kind of making up of a person on top of a hill riding a bike, that oh, the bicycle maybe is in the system. That would make sense. You could include or not include the person in the system. We'll talk about that in a second. But like the things that you include in the system would go there. So again, by what I mean by a system, it's just like the things that I'm analyzing the energy for, right? I'm analyzing the energy for the bicycle. I'm not analyzing, the energy for like a car next to the bicycle, right? So right in this case, I'm not including the person in there. The reason being on that is like I would, like let's say the person starts pedaling the bicycle. I could say, oh, this energy that's being added is from the person, or let me say maybe from the rider. Right, so that would be energy from outside the system, the rider, that's being added to our system, the bike. And so that's, if I included the rider in here, the problem that occurs is then I have to figure out, well, what kind of initial energy did the rider have, right? Did they have elastic energy, kinetic energy, gravitational energy? And it's probably not one of those things because people are fairly complicated. So we'll talk more about that in a second, but generally you don't include people in the system um, unless like you could replace the person with like a sandbag or something like that, right? Like if the person isn't interacting with the system, then or with stuff, then they're not adding or subtracting energy, then you wouldn't necessarily need that. Okay, if any energy is lost, so maybe we lose some energy, to friction or something like that, then that would happen. You would take care of that right here. And then what kind of energy do we end with? So, maybe now it's all gravitational energy, or maybe it's all kinetic now because we're moving fast, and we don't have any more gravitational energy because you're at the bottom of the hill or something like that. So that gives you an idea of basically the basic idea of how this works. So you have the initial energy and what type of energy is in this left-hand bar graph that you start with. So kind of at the beginning of the situation, you have any energy that's added or subtracted right next to this circle here, and then you would have the types of energy that you end with. The numbers matter. So like you can see that I wasn't very careful this time, but I have like 4 blocks here. I added 4 blocks. Let's say this, right? I lost maybe 3 blocks of energy. And I guess if I was careful, I would now have 5 blocks of kinetic energy. So you should be kind of careful about the number of the blocks that you have. So 4 going in, you start with 4, you have 4 more going in, so it's going to give you a total of 8. You lose 3 because of friction, and so now you're up to like 5 in the kinetic energies. So just kind of realize that also matters. So okay, so let's go ahead and take a look at the examples here. So you pull your little brother in a wagon up a hill at a constant speed with friction. So the question is, well, what do we put in? First up, we should think about what do we put in the system, right? Well, okay, fairly obvious, the wagon we should put in the system. And also like little brother should go in the system as well. Now, this is a really good example of like, okay, I'm putting a person in the system, but I could easily replace my little brother with a sandbag, and it wouldn't really change the situation at all, right? So my little brother isn't interacting he's not adding or subtracting energy. So I can put my little brother in the system. So let's see here. We go at a constant speed. So let's say we have some kinetic energy here when we start out, and we're going to have exactly the same amount of kinetic energy at the end. We know that's the same because we're moving at a constant speed, so the kinetic energy isn't going to change. We pull my little brother up a hill, so that means that we're going to have some energy going in here, and that's going to be from me. I'm just kind of making up the numbers in terms of like, note that I put 2 here and, 2 for kinetic and 2 for kinetic. I could have put 3, I could have put 4, it doesn't really matter. The 2 is kind of nice because I can add to that if I needed to, but I'm not going to need to. I put 4 bars of energy in. That's because I'm kind of thinking about it. That gives me a chance to be able to split it up a little bit. For example, I know that I'm going to lose some energy to friction. So I have energy from me going in. You should put little labels on it like that. Energy going in from me and out to friction, because it does say there is friction. So, and then we go up a hill, right? So we basically have 2 bars of gravitational energy. The way that I know that is, right, like I added, these obviously are going to kind of cancel each other out, the 2 kinetics and the 2 kinetics, because those just stay the same. So I've added 4, 2 of the bars came out. So now I only have 2 left. So those are going to ultimately end up as gravitational energy. So there you go. So just making sure your numbers kind of make sense. You almost think about it as like an equal sign right there, like the number you start with plus the number you added minus the energy, the energy you start with plus the amount that's added minus what's lost is equal to the number that you end with. So, basically 2 plus 4 is going to give you 6, minus 2 is going to give you 4 again. And so hence there's my 4. Okay, so let's take a look at example number 2. So example number 2, one quick comment on example number 1. Let's note that I did not put myself in the system, and the reason that I didn't is because I need me to be outside of the system, adding energy to the system, so that I could have it, right? I could have work done on the system, meaning, my little brother in the wagon. So I needed myself to not be in the system so that I could add energy from outside of the system. And again, the reason we don't put me in the system is if we did, then I would need to figure out what kind of energy do I start with. Do I start with kinetic, gravitational, elastic energy? But I'm a person, so I'm going to be, my energy is going to be complicated. Taking a look at number 2, we have, it tells us the system here. We got a spring and a cart. So here's our situation, right? We got a cart pressed up against the spring, and it's going to go through this loop-de-loop. We can assume that it's still moving, right? Because otherwise it would fall off the loop-de-loop at the end. So our initial situation is it pressed up against the spring with an initial velocity of 0. And then the final situation is it up the top of that loop-de-loop there. So as we think about it, like we're going to, right, we have some elastic energy here that we're going to start with. We got some gravitational energy here, and we also have some kinetic energy because we're also moving. So just kind of initially thinking about that situation. There's no friction, so there's not going to be any energy subtracted from the situation, and there's not really anything that's also adding energy to the system as the cart goes through this situation, right? So so we see that we are going to start with elastic energy. I'm going to go ahead and start with 4 bars because that gives me I could start with 3 if I wanted to, but 4 is a nice number, and that allows me to kind of split that up later. Again, there's nothing adding energy as the cart travels around this thing, right? There's no like little motors that push it along or anything. So basically, the amount of energy it starts with is that elastic energy. And I can include the elastic energy because the spring is in the system, right? If the spring wasn't in the system, then I couldn't include it as elastic energy. So no energy is added. No energy is also subtracted because there's no friction there. So no work done either into or out of the system. And so at the end, right at the end, we have some, we're going to have some kinetic energy and some gravitational energy. And I can split this up however I want, as long as it adds up to 4, right? Because it needs to be moving, so I got to have some kinetic energy. It's also up high because it's right up at the top of the loop, so it's got to have some gravitational energy there. So, all right, let's take a look at this one. Number 3 says same setup as number 2, except there is friction. So if we take a look at that, then this initial situation is the same. We're going to have elastic energy, right? That doesn't change. The one thing is that, so if there is some friction, we're going to, of course, lose energy to friction. So we put that there. And so let's think about that, right? We have to have the same amount of gravitational energy as we had before because we're up at the same height. So that's not going to change. But what is going to change is that I'm going to have less gravitation or less kinetic energy, right? I'm going to be going a little bit slower. So that one that I've lost right here, to friction, that's going to come out of the kinetic energy because ultimately the cart's going to be going slower at the top than it was when there was no friction. So there we go. Number 4, same setup as number 2 without friction. The system is only the cart. Okay, so this is kind of a weird thing. You wouldn't normally do this. You would almost always include the spring in the system, right? Let's note that we took the spring out of the system. The reason that we did this in this case is just to highlight like how these diagrams work. And so like if, right, the situation is exactly the same, we haven't, right, the energy still starts out of the elastic energy and it still ends up as gravitational and kinetic energy. Like that hasn't changed at all. Oopsies, sorry about that. That hasn't changed at all. So like, we still start out with elastic energy. We still end with gravitational and kinetic energy. The difference is that since the spring is not in our system, those 4 bars of energy are dealt with as work because it is energy that is outside of the system entering the system. So we'd say from spring here. And so it's still energy, like a still elastic energy. It just, right, since the spring's not in our system, it's being added from the spring to the cart. When that transfer occurs, which occurred in all the other situations, that's considered work now because it's energy that it was outside the system that's being added to the system, meaning now the system is only the cart. So from spring, that's now considered energy. No friction there. So we're going to end up with the same end situation where we have kinetic and gravitational energy, 2 bars of each, because, right, no friction. So there was no energy lost. Okay. Same setup as number 2, except without friction. This time, the system is only the spring, which means that the cart is not included. Again, this is a situation in which you would never really set it up this way because usually you're the one that gets to decide what's in the system and what's not in the system. if there's a cart, you're going to put the cart in the system. However, again, it's there to just highlight how these like LOL graphs work, these energy bar graphs. And so if the spring is in the system, we start out with elastic energy, and we can plot that because the spring is in our system. But then when it gets transferred to the cart, just all the energy gets transferred to the cart. Just like that, I would have no energy in the end, because in the end, all the energy is in the cart. The cart is not in the system. And so that's pretty much the way that works. So these are a little bit tricky. You're going to get used to, you'll get used to them as you practice them. There's also many ways in which you can do it. So just because, the way that I do it doesn't necessarily match the way that you do it, because, right, you're ultimately choosing the number of bars that go into each one. That's not really the important part. The important part is that you can just kind of track the energy. So you can say, like, let's go back to ones that maybe are more the way you would normally set it up. Like let's take number 3 right here. It's tracking like, okay, I start out with elastic energy, I lose some energy to friction, I end with kinetic and gravitational energy. Like that's ultimately, that setup is the most important part, because that's going to allow us to write equations later on. So that's the part that really, hopefully, that's the important part, right? Don't get too hung up on the numbers. I mean, your numbers should match, but and be logical, but that's not the really important part, right? So anyway, as you work on this and as you practice this for your homework assignments, hopefully it'll kind of make more sense. But thank you very much for watching, and as always, let me know if you have any questions. Thank you. Bye.